So today we're going to be talking about some more applications of integration to physics, and we're going to be computing work using integrals. So work is just defined as force times distance, but we can also determine this using an integral because sometimes the force is not constant and it changes. So here we're just pretty much doing our normal integral from a to b of a function for the force, and then dx is the change in x as we go, or it ends up being the distance. So we're going to start with a force of 5 pounds stretching a spring, and then we're doing the work, finding the work done in stretching the spring to 6 inches beyond its natural length. So in order to do this, the first thing we need to do is figure out something called the spring constant. So for a spring, the force, this is called Hooke's law, some constant k times x. So we have to figure out our spring constant, k. So this is our spring constant. So in order to figure this out, we have to do a few things. Our force is 5 pounds. It's k. And then we know the spring is stretching 4 inches. So normally we need that in feet though for this to work. So 4 out of 12, so 4 inches out of 12 is how many this is in feet. How many inches are in feet?
Excuse me, I've just seen another email that needs to be.
So that just means that 5 equals 1/3 k if I reduce that 4/12. That means that k equals 15. So now my work integral, my force function, let's start with that first, is just 15x. So my work integral, my work done, is going to be integral from 0, 6 inches is a half of a foot, so I'm going to put 1/2 up here. And then I've got my function, which is 15x dx. Then I just do this integral. So just like we did before, this becomes 15 over 2 x squared, and I'm evaluating at 0 and 1/2. And then I plug in those two numbers. So I have 15 over 2 times 1/2 squared minus 15 over 2 times 0 squared. And 1/2 squared is 1/4. 15 times 1 is 15. 2 times 4 is 8. And that would be foot-pounds is my final unit for work. Because my force is in pounds, my distance is in feet. Alright? Same kind of idea here. Alright? Now, since the weightlifter is lifting 250 pounds, a distance of 20 inches, the work done is measured in foot-pounds. This is actually a lot easier because we don't even really need the integral here. We can just do force times distance, because the 250 pounds is staying 250 pounds the whole time. So we just need to change 20 inches into feet. So my work is going to be 250 pounds times 20 inches out of 12 per feet. Alright, and then just multiply this out. So that's going to be 5,000 on top of 12, which reduces to 1250 over 3 foot-pounds. So sometimes they're this easy because the force is constant. Sometimes it's a little bit more tricky because the force changes everywhere. And if you want to approximate this, this is what you get, 416.67 foot-pounds. Right. Sometimes our force function is a little bit more complicated. So we've got a rocket to start with that weighs 10,000 pounds at launch. Now, as the rocket gains altitude, it loses weight as the fuel burns. So we're going to assume that the rocket loses 1 pound of fuel for every 15 feet of altitude gained. Explained why the work done raising the rocket to an altitude of 30,000 feet is this integral from 0 to 30,000 of 10,000 minus x over 15 dx, and compute the integral. So, if we look at this integral, hopefully we can see that the 10,000 comes from the launch, so 10,000 pounds at start. And then as we gain altitude, we're going from 0 to 30,000. That's where 0 and 30,000 come from. Why do I have minus x over 15? Because I'm losing 1 pound of fuel for every 15 feet of altitude. So if I do x being my number of feet divided by 15, that gives me 1 pound of fuel every 15 feet of altitude gained. So then we can go ahead and do this. Again, we got the integral from 0 to 1 here. And then we've got our function. And we're going to just evaluate this integral. So let's pull that 800 out and go ahead and multiply the x in. So this ends up being x minus x squared with the dx. That's 800. And then I've got just x there, so that's 1/2 x squared minus 1/3 x cubed. And we're going from 0 to 1. Alright. So that's 800. And then with the 1, I've just got 1/2 minus 1/3 here. So that's going to be 800. 1/2 minus 1/3 is 1/6. Now, here's the problem. I'm not in foot pounds. I'm in mile pounds right now. So I got to multiply this by 5,280 feet in 1 mile to finish up. Alright, that'll cancel the miles out. And that leaves me with 704,000 foot pounds. That was sloppy.